Hi everyone. So in this video, this is a very quick and short video for solving the system of linear differential equation. We did this in the last two slides in part 4, so I will repeat this in more like details. Maybe it was so quick with no audio in the last one. So let's see what this system of linear differential equation will look like and then how to solve it easily using Laplace transform. So first, we have system of linear differential equations. So here we have the system. Still, we are working with linear differential equations. So I have, for example, I have two dependent variables, x of t and y of t, not one, right? As previously performed in the regular linear differential equation. So we have couple or three or four multiple of these linear differential equation with some parameters. Here we have x and y as their parameter is t. So we have some function dx by dt, and we have dy by dt. We have x and half y, and also we can have this t, which is the independent variable. This can be one equation. If we have two variables, right, this like this case, we should have another one to have some unique solution. So for example, we can have another equation between, again, dx by dt, dy by dt, x, y, and some function of t. This is the second relation. And the only difference is these constant like a, b, c, d, e. And we may have another set of different constant, L, M, N, Q, P. And all of these constants may be numbers, could be some kind of something we could carry out some operational properties using Laplace transform properties. And then we will end up, like if we are using Laplace transform, so all these derivatives, d by dt, as we mentioned previously, it will be as we have here some variables, so it will be Laplace of this variable. So this is all the case minus this variable at t equal to 0. So this condition should be given as what's called initial value problem. So again, this is initial value problem. And then we can dy by dt, it will be algebraic equation in y and s. Dx by dt, it will be algebraic equation between s and x. So all of these parameters at the end, it will be some kind of something multiplied by x, another thing multiplied by y, equal some function in s. And then we have multiple of these equations. Solving them, we can get our value here, which is x and y. Getting Laplace inverse, we can get finally this x as a function of t and this y as a function of t. So with this brief introduction, let's move on some real examples. Let's repeat what we did before. We have equation dx by dt equal minus x plus y. And we have another differential equation dy by dt equal to x. And given the initial value problem, the initial conditions, which is x at t equal to 0 and y at t equal to 0 equal to 1. So to solve this equation, again using Laplace transform, we can end up with this equation right now, which is s x of s minus x of 0 equal minus x of s plus y of s. The second equation will be s y of s minus y of 0 equal to x of s. Substituting with this initial condition, x of 0 is 0, y of 0 equal to 1. This will give us the new two sets of equation. We have this x of s, and this multiplied by s plus 1. And we have here minus y of s, and this equation equal to 0. The other equation is we have this 2x of s, and we have this minus s multiplied by sy of s, and then it will be moving everything to the right side, so we'll end up with equal minus 1 in the right hand side. So here, this is the two equations, and just make some numbers here. This is equation number 1, this is equation number 2. We need to solve both equations. We can see this like we can solve this equation by several methods. So here, let's assume we can seek something different than we did in slide, like in the part 4 videos. So here, let's assume I will multiply equation number 1 here. I will multiply, I need to cancel out like this y. So I will multiply number 1 by s, and then I will do this 1 minus equation number 2. So I will do this subtraction. So let's do this. So I will end up with here s multiplied by s plus 1, x of s minus 2, and these all the parameters multiplied by x of s. Y will be cancelled out. I will multiply s in the 0 term, so it will be 0. And the other term, it will be minus 1, so it will be 1. So here we'll end up with this x of s equal 1 over s plus 1 minus 2. So here let's just do this multiplication. So this s squared plus s minus 2. This can be like obtained using partial fraction. So this is s plus 2 multiplied by s minus 1. Here is 1. So it will have something over s plus 2 and another thing over s minus 1. To get this numerators, we will substitute s equal minus 2, so it will be 1 or minus 3. I'll substitute with the other thing with s equal to 1, so this one will be 1 over 3. This will end up as x of t, which is Laplace inverse of this x of s, will be equal minus 1 over 3 e power minus 2t plus 1 over 3 e power t. And this is the value of x. The second question will be how to get y. So again, you have to get y using either substitution in the t domain in the differential equation itself, or in the s domain you can use any function like this y of s from equation number 1. You can get this y of s equal s plus 1 multiplied x of s. Means it will be s plus 1 over s plus 2 divided by s minus 1. Again, a simple partial fraction right now. So substitute by s equal minus 2. It will end up, this is minus 1, this is minus 3. And substitute s equal to 1, this will be 2, and this is 3. So we'll end up here with this y of t equal 1 over 3 e power minus 2t plus 2 over 3 e power t. So here, this is our y of t. And we have the sample check. So we're given this x of 0 equal. And we have also this y of 0 equal some value. Just substitute. So this here at x equal to 0, this will end up with 0. This is perfectly correct. And the other one, substitute t equal to 0 in y, it will end up with 1/3 plus 2/3, so this will be equal 1. And that's correct. So just this as a sample check that we are doing the right thing. Again, let's see here what we have done in this example. We have dx by dt equal a function between x and y, and we have dy by dt, another differential equation equal to x, and we have this initial condition at t equal to 0 for x and y. Using Laplace transform to transform these differential equation into algebraic ones by substituting by these initial conditions, we'll end up two sample equations between x of s and y of s. You are free to use any method to solve these linear algebraic equation. So this is a system of two linear equations. We end up with this x of s, we solve it, equal 1 over some quadratic equation in S. This is very special here. We can factorize this one, so we can use a partial fraction. If not, we can use the complete squaring method. So here we can use this partial fraction. We'll end up with some fraction over s plus 2 and another fraction for s minus 1. It's some easy Laplace inverse. Both of them are exponential from the table, e power minus 2t and e power t. For y, I can get y from this one, from the second equation, or from the first equation, if we are if it's much easier to use the S domain. The other case, one can think about it. Just use this equation here, dx by dt equal minus x plus y. So we have x, and we have dx by dt for sure. It's the derivative. So I'm substituting by x and dx by dt, I can deduce y. So another method, just I can write it down here. This y also can be obtained using this y equal dx by dt plus x. And if you are doing this derivative from this one, added to the value of x itself, we'll end up with the same thing. So that's how we can solve this certain linear equation. And let's move on and solve another example also. We have the second example here, dx by dt equal x minus 2y. And we have dy by dt, the other differential equation in y, equal 5x minus y. And given the initial conditions, x at t equals 0 equal minus 1, y at t equals 0 equal 2. So again, to solve this one using Laplace transform, we'll have this equation here. It will be s times x minus x of 0 equal x of s. I'll leave it as big letters here, capital, so this minus 2y. The other one, it will be as 5s minus y of 0. So the small letters, it means it's still in the t domain. And 5x minus y. It's given that this x of 0 equal minus 1, this one equal 2. Simplifying both equations, I will end up with some coefficient with x, which is here as minus 1. And another coefficient for y, plus 2y, equal on the other side minus 1. And this is the first equation. The second equation, we have this 5x. And we can put this here minus sign. And I will move everything to the left-hand side. And we have y as plus 1 y. And this equation here will be equal to. So solving these both equations right now, it's two linear equation between x and y. And then, sorry, this is not minus, this is plus. So solving both equations right now, I'll end up getting this x and y as a function of s. So let's do so. So this is our first equation. This is our second equation. One of the methods, I can get rid of this y or get rid of x, so it doesn't matter. So I will multiply the first equation by s plus 1. And the second equation, I will multiply it by 2 and subtract both equations together. So if I can do this, the first equation will be, or the coefficient of x will be this s minus 1 multiplied by s plus 1 minus the second equation multiplied by 2, so it will be 10. This is a positive sign. This is the coefficient of x. Coefficient of y will cancel out, so this will be 0. The other term will be minus s plus 1. And this one will multiplied by 2, so this one will be minus 4. So this one, it's nothing but minus s minus 5. So x here, doing simple, like doing some quick simplification here, it will be this s squared minus 1 plus 10, which is here minus s minus 5 over s squared plus 9. So again, doing this just partition here, this will be s over this s squared plus 9, and we have this 5 divided s squared plus 9. Again, this is very straightforward, so x of t, it's Laplace inverse this x. The first one, it's from the table, very straightforward, cosine 3t. The other one, again, it's from the table, sine 3t, but should have the 3 in the numerator, so I will divide by the 3, and then this is our x of t. Again, you are free to use whatever it's easier to get y. So here, let's get y from the first equation, like from this linear differential equation, change the method. So here, I can say this y will be equal x minus dx by dt, and all of these terms divided by 2, multiplied by half. From where? From the first equation given in our two equation in the system of linear differential equation given in this problem. So this will be half. X is minus cosine 3t minus 5 over 3 sine 3t minus dx by dt. So dx by dt will be, this minus will be plus, and then 3 sine 3t, and then this will be 5 cosine 3t. Again, we'll do this. 5t will be equal this half, and then we have minus cosine 3t, and we have plus this 5, so it will be 4 cosine 3t, and we have the sine term, we have minus 5 over 3, minus 3, which is 9 over 3, so this will end up 14 over 3 sine 3t. And here, this is y of t. The simple check as usual. What is the value here of x of 0? So x of 0, for sure sine will be 0, so it will end up with cosine equal to 1, so it will give you minus 1. And what's the value here of y of 0? So simple substitution, sine will be 0, and then we'll end up with this 4 cosine divided 2. 4 divided 2 is equal to 2. And then again, it's correct. So, hope this like quick introduction to solve this system of linear differential equation. It's more clear than the previous one, and it has some kind of ideas how to solve any kind of this linear system of differential equation. And thank you for your attention.